Okay, I think most of us are here. Can you guys hear me?
Yes, doctor.
All right. Yeah. Thank you. Thank you. So I think yeah, we're ready to begin. If you guys agree. We talked about a couple of things last time regarding the design in especially silicon solar cells. Okay, so let's go over them quickly. Some of them actually we covered back in solar PV, and some of the I think the designs we introduced for the first time, in the last lecture. So one of the things we mentioned in solar PV is the design is the barrier contact. Okay, so remember, for barrier contact, we have to do additional processing on the silicon surface, and then we can bury the electrode into actually the silicon wafer surface, so that we reduce the shading loss from silicon. Okay, and then another new designs that we talked about last time, is actually the back surface field layer. Okay, the back surface field layer. The idea is that typically we want the electrons and holes after the separation actually to go in their own direction, to go in separate directions. Okay, so this typically means that we want the electrons to go towards the n-type side, the emitter side, while the holes actually to come out from the p-type side. Okay, but then sometimes you may have electrons wandering in this direction, and then you have holes also wandering in the opposite direction. But typically we wanted to eliminate these unwanted carriers. Okay, and we want to basically push them back in the correct direction. So how can we achieve that? Because otherwise, if we let them continue in this way, essentially they will be trapped by the surface recombination. And also at the same time, if you have electrons and holes that moves in the same direction, essentially you are talking about they're canceling each other in terms of the current. Okay, so how can we achieve that? Very simple. We can introduce a additional layer near the back surface or near the front surface. If it's a near the back surface, this approach or this design is called the back surface field. If it's near the front surface, we call it this, the front surface field. Okay, and then the layer we inserted typically is actually the same type of a semiconductor as in that part of the PN junction. Okay, what I meant is that in the base layer, if we want to insert a back surface field layer, we typically also insert the same type, that is the P type. Okay, but at the same time, you are going to add the additional doping level. Okay, so it's going to be P plus for the back surface field. And then, how are we going to visualize the energy band? Very simple. Remember, this is a similar process as the PN junction. Okay, so remember that if you want to differentiate the energy band diagram, the electric field difference, you start from diffusion. Okay, you start from diffusion. So for the back surface field layer, the P plus layer, initially you have more holes compared to the base layer. So initially we are going to see holes actually diffuse from the back surface field layer to the base layer. Okay, and then this essentially is going to create actually locally a space charge region, just like a regular PN junction. Okay, so we're going to expect negative space charge from this side and more negative space charge compared to the p-type side. So relatively speaking, we're going to see negative and positive appearing actually in the interface for the back surface field. Okay, and then this means that locally you are creating an electric field actually that is attracting electrons. Okay, that is attracting electrons. So this also means that if it's attracting electron to the left side, then locally speaking, the left side of this junction will have a lower electron energy compared actually to the right side. Okay, so electrons actually will have the tendency to be pushed back towards actually the base layer. So and this is exactly what we wanted in the back surface field. We want the back surface field to repel, to push back the electrons. Okay, so you can apply the similar method to analyze the front surface field. Essentially, we for the front surface field, we would like to insert a layer near the front surface that has even higher doping level compared to the emitter. Okay, and in that way, we can try to push back the holes actually from the front side. Okay, so this is actually something new we introduced last time. And here you see an example of the front surface view. Okay, you see an example of the front surface view here in this example. Okay, so moving on. And then we also cover the surface passivation method. Okay, remember we were saying that typically in solar cells, you want to pay additional attention to any surface because typically at this kind of surfaces, you have a very high surface recombination. Okay, and most likely you are going to lose a significant portion of carriers near the surface. And to reduce this surface recombination, we can passivate the surface by closing the origin of the losses. The origin of the losses is typically that we have a lot of open or dangling bonds near the surface. And if somehow through additional bonding or through additional treatment, we can close this bond, and then in this way we will be able to reduce the surface recombination. Okay, so for silicon, a very typical method to passivate the surface is by attaching oxygen or the oxygen atom to the surface, and then we can form very stable silicon dioxide. Okay, so this is actually what you see in the picture here. We can put the silicon surface through high temperature with the air, and then the oxygen will combine with the silicon to form silicon dioxide. Okay. But keep in mind that the silicon dioxide is typically an insulator. So you don't want actually the surface passivation to affect the conductivity of your solar cell. Okay, so which is why you see that the silicon dioxide layer is covering actually the rest of the area except for the electrode area. Okay, so in this way, we will be able to suppress the surface recombination, and we should be able to passivate the front surface and the back surface at the same time, and this will greatly increase your solar cell performance. Okay, so that is the surface passivation that we also introduced last time. So continuing from last time, what else can we do in silicon solar cell that can further increase the performance? One additional design that you can do, and probably you already realized this design from the previous diagrams, because the previous slide they already have some examples of this, is to use the so-called point contact. Okay, point contact. Remember that originally, if we talk about the solar cell, for the back surface, we used to have so this is the silicon base. And for the back surface, we used to have a whole layer of metal near the backside. Okay, and this is our electrode. Okay, this is the back electrode. But then the problem is that considering that we have a large area of the surface termination here, so the surface recombination on the back surface is going to be very high. Okay, it's going to be very high because you have a large area of open surface between the silicon and the metal. So considering this, we're going to see a lot of losses actually on the back side and also in the front side as well. Okay, how can we reduce that? Well, if you can guarantee the conductivity, with the electrode, if you can guarantee the conductivity of the electrode, how about we shrink the electrode into single or into several points? Okay, into several points. So this is the idea for the point contact design. It's actually closely related to the surface passivation. So if we limit the electrode area to these points, okay, for the rest of the area, we can passivate them. We can close the open bonds with the passivation layer, with the oxide layer, and in this way, together, if we combine these two approaches, we can actually further reduce, the surface recombination. Okay, and in this way we can hope to increase the solar cell performance. So this is the idea for the point contact, and actually you will be able to do the point contact for the front surface as well as the back surface. Usually at the same time, it's possible. Okay, so that is one more additional designs you can do. And then in solar PV, we also after we talk about the battery contact. the barrier contact is used to reduce this the front surface optical shading losses. We also mentioned back in solar PV, it is possible for you to shift actually the positive and negative contact, both of them, to the backside. Okay, this is the so-called all rear contacts. Okay, all rear contacts. So everything on the backside, nothing on the front side. So actually, this solar cell is a flip, if you remember. But now in this case, we have the positive contact here. We have the common negative contact here. Okay, and the positive and negative, they are both shifted actually to the backside. Okay, and then in the front surface, basically we have a zero obstacles. We have a zero obstructions. And in this way, optically speaking, you can have a almost a perfect, solar cell. Okay, the solar cell, optically speaking, will be almost perfect. There is no shading losses, zero shading losses from the fingers. And obviously, if you shift, the positive and negative all to the backside, then obviously you have to use the point contact method. Okay, because you cannot have the front contact, touching the the back contact. You cannot have a positive touching negative because immediately you are going to have a short circuit in the solar cell. Okay, so this means that on the back side, all the contacts have to be shrink into point contacts. Okay, into point contacts, just like the example here. We have the N-type contact, we have the P-type contact, and supposedly the solar cell is basically between them. Okay, the solar cell will be between them, and on the front surface, we have basically no obstacles. We have zero shading losses. So this is the idea for basically the all rear contact solar cell. Okay, or sometimes we call this the full point contact design. Okay, the full point contact design. But obviously, there are some challenges we have to overcome with this design, because this design is actually very different from the typical solar cell design, and therefore there are a lot of difficulties associated with this new design. One of the things we have to consider now is that the RPN junction is actually positioned horizontally rather than the typical perpendicular structure. Right? Typical solar cell, we have the N plus emitter, we have the P base, and basically the line is incident vertically like this. Okay, and our PN junction supposedly, or our space charge region supposedly is actually in the vertical arrangement. But then in this case, our PN junction, technically speaking, is located horizontally between the point contacts. So this actually puts additional restrictions actually on your solar cell, especially on the layer, on the thickness of the silicon layer. Okay, because remember, you have to consider the diffusion length limit in solar cells. Okay, and typically we cannot put the very thick silicon here in this kind of a solar cell, because otherwise you are going to have a lot of losses for the carrier diffusion to the backside. Okay, so this design is actually optically speaking is very attractive, but at the same time we have to sacrifice other properties, other performance, in order to actually have in order to show an overall improvement in the solar cell. Okay, the record efficiency for this design used to be more than 24%. So this is actually a very this is an excellent design, but at the same time, as we said, you have to sacrifice a lot of other performances, and also the in terms of the cost of this design is not very affordable, because you're talking about very complex manufacturing techniques. Okay, so that is the full point contact design, and then basically there was a prototype silicon solar cell, or you could say that there was a champion silicon solar cell that combines most of the high efficiency designs into one prototype, into one solar cell. Okay, so this champion design is called the PER solar cell. Okay, the PER solar cell. PER stands for passivity emitter rear locally diffuse solar cell. Okay, and this is actually the schematic of the PER solar cell. You can spot from the diagram that several of our designs that we mentioned before is actually combined into this design. So try to see what can you see from actually the diagram. Okay, what can you notice? What are the designs that we mentioned before? I gave some hints here. So for instance, you can see from the pyramid structure here that we have the surface texturizing incorporated into the front surface. Okay, and then if you notice on the back side, we have the point contacts. Okay, we have the backside point contacts. And then on the front side also the contacts are in points. Okay, remember these are basically used to reduce the surface recombination as much as possible. And then with the point contacts, we also have the passivated surface, right? We have the passivated surface, passivated front emitter and passivated backside base layer, because you can notice that there are oxide layers in the front side and in the back side. Okay, so in the area where you don't have the point contact, we have incorporated the surface passivation layer to reduce the surface recombination. Okay, and then if you further notice the P plus here and the N plus here, these guys are the front and the back surface fields. Okay, the front and the back surface field layer, basically to further reduce, or to further repel the carrier losses from the respective electrons. Okay, so the Purcell or the prototype at the time of its invention actually was able to achieve the best efficiency, in silicon solar cell development. Of course, nowadays we have a better designs that is improved on top of the PER design. Okay, but this was sort of like a milestone in silicon solar cell development. So these are the parameters of the Purcell, at the time of its invention. Okay, so we mentioned earlier in this chapter that we typically prefer, whenever we talk about solar cells specifically, we prefer to use the current density unit. Okay, so to give you an idea, what was the best current density that we are able to achieve in the Purcell? Actually, it's around 42. Okay, 42, and typically the milliamp per centimeter squared. This is a very typically widely used unit for current density. You can check for basically papers working on solar cell. Most of the time, they prefer to use this unit. Okay, so that you need to have an idea about under this unit, what is the typical value we can expect from a solar cell. Okay, so 40 plus milliamp per centimeter squared is a very good value. Okay, it's a very good value. And then depending on your solar cell material, sometimes for instance, as far as I know, for third generation, we typically have a lower performance. So for organic solar cell, typically the JSC is around the range of 10, maybe to 20 milliamp. Okay, 10 to 20 milliamp per centimeter squared. And then for the newer solar cell, for instance, for perovskite solar cell, typically the short circuit current density is it can go from 15 to over 20, maybe less than 30, something like that. Okay, so you need to have an idea. And then for silicon, typically it has even higher performance. So here we're talking about 40, but it's also very common. You see 30 or between 30 to 40 milliamp per centimeter square for the current density. Okay, for silicon fill factor is usually a very excellent parameter. So for the Purcell, it was 83% fill factor. While the open circuit, it was 0.714 volt for the V open circuit. That is very impressive, considering that most of the silicon solar cell we have less than 0.6 volt. Okay, for V open circuit. Of course, the good performance comes at the sacrifice of the cost. Okay, so the Purcell actually has over 100 process steps in the fabrication. So it is good for demonstrating how well we can do in solar cell performance. But on the other hand, these many processes, these many steps is actually unacceptable for mass production, for industrial production. Okay, so which is why nowadays in the market, most of the solar module we're using, they don't exactly have a 25% efficiency. Most of them, they have a lower than 20%, because at the end of the day, you do have to find a balance between the cost and the performance. Okay, so the cost and the performance, the trade-off that is going to be a constant theme throughout actually the lectures, throughout Solar PV and throughout this lecture as well. So keep this in mind. Okay, so that is actually the first cell. So at the end of this chapter, I just want to do a very quick summary of the major losses in solar cells, specifically in the standard silicon solar cell. Okay, and I think after this chapter we have a basic idea what to do, if we want to reduce certain losses. Okay, so first let's look at the losses. Basically, as we said, solar cell is a device that combines optical and electrical performance. So typically you have to look at the losses from both sides. Okay, some losses are optical losses, and then some other losses are electrical losses. Okay, so we have the graph here to help you with the understanding. So basically, for the optical losses, what kind of losses we may encounter? That will include the surface reflection losses. Okay, so some of the light you can simply not absorb; they will be reflected away from the surface. And then we have also the shading losses. Okay, this is not, in the context for solar cell, the shading losses is different from the module loss of module shading or panel shading we talked before. These shading losses is talking about typically the shading from the fingers. Okay, because from the fingers, typically these shading losses you cannot avoid. We have to always consider the design for the fingers, and then how we can reduce these kind of shading losses as much as possible. Okay, and then there is also the transmission loss. Okay, this actually depends on your solar cell the optical performance of your solar cell. So we said that in this chapter we taught you how to do the calculation, right, for a typical solar cell material. So once the light is incident on the solar cell layer, part of the light will be reflected, and then inside the solar cell material, we understand actually from our theory that the irradiance is going to experience an exponential decay. Okay, so the horizontal is actually the depth of the material. Okay, so we're going to see exponential decay of the irradiance. So if your solar cell is thick enough, then this decay will decrease to a minimum level. But then if the thickness is limited, specifically if it's limited by the diffusion lens, as we mentioned later, then you may still have some part of the light that will escape from the backside. So this part will be your transmission losses. Okay, that will be your transmission losses from the backside, especially if the solar cell is not thick enough at this wavelength. So basically these are the major optical losses. And then what can we do to reduce these optical losses? For the reflection losses, we mentioned that typically there are different approaches. We can use anti-reflection coating, okay, and we can also do the texturizing to roughen the surface, okay. For the shading losses, if we want to reduce the shading losses on the front side by the front electrode, we can use a barrier contact, okay, to bury the electrode into the silicon surface. We can also use another design that is the all rear contact design, where we shift the positive and negative, everything actually to the backside. Okay, so that is another solution. Actually, the all point contact design of course provides a zero shading losses, but remember at the same time this design is actually more complex. Okay, it's more complex. And then for transmission loss, we already mentioned the solution, even though it's not written here. But overall, for your solar cell, you have to find a balance between the electrical diffusion length and the optical absorption efficiency, okay, by basically mainly controlling the thickness, okay, controlling the thickness, and also by controlling the quality of the material. You want to make your material, that has a higher, as much quality as possible, that has a longer diffusion length, so that you can increase the thickness within the certain limit, and then you can increase also the optical performance. Okay. So that is basically how we deal with the optical losses. And then we have the electrical losses. Now we come to the electrical losses. Okay, what are the electrical losses that we can expect in solar cell? First of all, there are the ohmic losses. Okay, that includes the ohmic losses or the resistant losses from the contacts. Okay, from the silicon resistance, and then also from the interface resistance. So between silicon and the metal at the interface, there is also typically certain amount of resistance that is associated with the interface. Okay, so for these contact losses, typically you have to use a high conductivity material. You have to change or modify your design so that from the shape of your electrode, from the shape of your fingers, they have a sufficient dimension. They have a sufficient width and the thickness, so that they will provide you with the minimum resistance. Okay, and for the interface, if you have some issue with the interface between two materials, especially if they don't form a very conductive interface, another solution is that maybe you can insert a third layer in between the two materials, so that you form a smoother interface. You form a more conductive interface from there. Okay, so there are different strategies where you can actually improve this kind of performance. And then a major electrical losses for a solar cell is obviously the recombination losses. Okay, recombination losses. Recombination losses that can come from bulk recombination losses. Okay, so in this graph is called volume recombination losses, but it is the same as the bulk recombination losses. That means recombination happen inside the semiconductor material. Okay, so what can you do to reduce the bulk recombination losses? Use a higher purity material, use a higher crystallinity material. Okay, that has a higher order of a degree that can decrease the number of defects. Yeah, and then for the for the material processing, if you are using dope semiconductor, okay, you can try to increase or improve your processing so that the defects you introduce from doping, if we can reduce the defects, then we can reduce these kind of bulk recombination losses. Okay, and then another also equally important recombination losses, source of recombination losses, that is the surface recombination loss. Okay, so how do we reduce the surface recombination loss? We can use front and the back surface field that we just mentioned. Okay, we can also do point contacts, right, to reduce the area of the surface. And then if we combine with the surface passivation, then we can have a much better performance from the surface recombination. Okay, so this is the idea, or this is the like a quick summary about actually the different losses that we cover in this chapter, and how can we increase the performance of our solar cells. Okay, so that's basically the end of this chapter. We reached the end of chapter 1. Here we have some references. If you want to read more about this topic, you can follow this list of suggested references. Okay, so as we said last time, I think during our next lecture, we'll try to have a quiz, right? That is basically covering this chapter 1. Okay, that is covering this chapter 1. So I just want to go over things very quickly with you to prepare you, I think, for the quiz. Okay, discard. All right. So I know that we cover a lot of actually. I think theory and the equations in this chapter. The quiz is going to be a closed book. Okay, the quiz is going to be a closed book. But then I'll just go over these very quickly with you so that you can understand what to expect. Okay, what to expect here. Let me share the screen again. Okay, here we go. So basically, most of the equations actually we will provide you with the question, okay, during the quiz. So this includes, for instance, I think So for the optical performance, for these exponential decay, I think these equations are very simple. So I'll expect that you need to understand them. You need to know how to use it. Okay, and you need to memorize these basic equations. And then I think for the absorption efficiency, I think you can derive that with your understanding. Basically this diagram, I think, is the main diagram you need to use. Okay, and then from there, we can find basically all the solutions for all the irradiance that we have here. Okay, so this is the penetration depth. It's okay. This is okay. The absorbance, you need to understand. You need to know the equation, obviously, right? So it's not difficult. Basically, we're talking about the log. You just have to remember that this is the log ratio, right? From the inverse of the transmission. Okay, so it is actually connected to what we learned before, and then we come to the p-n junction or the semiconductor physics. Okay, so for these equations, there is no need for you to memorize them. Okay, because mainly we went through these slides just to show you in general how to approach the solving of a semiconductor. And since we didn't do any actual solving, so we will not be having typically questions on solving these equations. Okay, so there's no need for you to memorize this. I may give you one or two equations from this slide, and then ask you what are the meanings for this and this parameter. But other than that, I don't need you to memorize the full equation. There is no need to do that. Okay, you just need to make sure that you understand what is a continuity equation, what is the meaning of a transport equation, things like that. Okay, but you will not be required to write the full equation. Definitely not. Okay. Yeah, and same thing here. We talk about generation rate, recombination rate, but yeah, you don't need to memorize these equations. Okay, you need to understand them, that's for sure, but no need to memorize them. Okay, diffusion length also, you need to know the physical meaning, but at the same time, if I need you to do calculation, I will give you the equation. Okay, right, and then the solving, yes, same thing, and then we come to, I think, the physics in solar cells. This is okay. Quantum efficiency, obviously I need you to understand, the basic concepts. Okay, and this is a simple equation, so you need to know that. Okay, you need to know that. Internal quantum efficiency, same thing. It's a very simple equation. Okay, so obviously you need to understand that. And then this, we come to the spectrum sensitivity. For this, there is no need for you to memorize it. And overall, it's a very simple equation after all. But we will provide this equation for you if necessary. Okay. And then the model, for the electrical model for solar cells, I think it's relatively easy enough. But yeah, if you want, yeah, I can provide this in the questions, in the exams, okay, in the quizzes. Yeah, it shouldn't be too difficult. And then after that, I don't think we have any further equations. Okay, so is there anything that's not clear? I think, yeah, would you guys prefer to have the quiz on Thursday or next Tuesday? Yeah, let me know. Would you like us to continue with our chapter 2, or we will be, if we have the quiz on Thursday, we will be still, use maybe half the time to cover chapter 2, and then the other half for you to do the quiz. Okay, and the quiz is going to be on Blackboard with the lockdown browser, but it's going to be a shorter version of the quiz. Okay, what do you guys prefer? Let me know. Next Tuesday, okay. I don't suppose anyone that favors Thursday. Right? All right. So in that case, yeah, let's try to do this next Tuesday, since that the majority wants to do that, no problem with me. So we will be, I think, going over or actually crossing over to chapter 2. Okay. And then next Tuesday, just be prepared for a closed book quiz on chapter 1. And as I mentioned, these equations, the simple ones, yes, you have to memorize them. It's not that difficult. I'm positive. The others, as I mentioned, you don't have to memorize them. Okay. And we're not going to go over a lot of questions. Just a couple of questions to test your understanding in this chapter. Okay. So if this is okay, let us continue on to our chapter 2. Okay, if it's okay with you guys. So in this chapter, most of the things we discuss here, I think this will be new stuff. This will be new things that we didn't cover back in Solar PV. And I really actually prefer this chapter because I think this chapter opens up, I think, your vision of actually what we can do with the solar cell, with the solar PV. Okay. Specifically, we wanted to talk about the different measurements, the different characterizations that you can perform on a solar PV. That will give you a lot of new insights, new information about actually this specific device. Okay, so this is actually a chapter I personally like very much, and also because most of the stuff I have done the measurement also personally before, or actually doing now. Okay, so I hope that this chapter will be will be helpful to you, and at least it's going to show you some interesting insights. Okay, so what is being covered in this chapter currently? We would like to go over the measurement for solar cell efficiency. Okay, but then we're going to focusing on actually more on the details of the efficiency measurements. Okay, specifically, we want to show you how we can conduct an accurate measurement on solar cell efficiency. What are the basic requirements, and what can we do to achieve these requirements? Okay, so that is basically the first part. And then one of the new things that we cover in chapter 1 is related to the quantum efficiency. We already mentioned that quantum efficiency is different from the energetic efficiency. Okay, so this here is the energetic efficiency, but at the same time we also mentioned the quantum efficiency. Okay, the quantum efficiency. So if we want to do a quantum efficiency measurement, what are the requirements for the system setup? Okay, and then we're going to show you from the external quantum efficiency. How do you go from external quantum efficiency into internal quantum efficiency? Because both quantum efficiencies we covered them in the last chapter. Okay, and then at the end we would like to also show you a very useful feature from the quantum efficiency, that from the EQE, from the external quantum efficiency, it is possible for you actually to correlate with the short circuit current or short circuit current density from the same solar cell. Okay, so there is a link, there is a direct link between the EQE and the short circuit current density. And if you have the EQE, actually it's actually very easy for you to predict what's going to happen for this solar cell under the sunlight. Okay, under the AMS 1.5 G spectrum. So actually it's actually a very useful thing to learn, a very useful thing actually to know. Okay, so that is actually actually what we have in mind for the quantum efficiency part. Okay, and then we also like to show you at the end of this chapter that there are different measurements that can be performed on the solar cell that will give you different kinds of information. Okay, so for the energy efficiency or energetic efficiency, typically we apply the IV scan. Okay, or the IV curve. We measure the IV curve typically under under illumination. Okay. But then we also like to show you that if you perform IV measurement in the dark, this is also meaningful. This is also helpful. It can show you additional features or additional information that you will not be able to find under illumination. Okay, and then besides the dark IV, we would also like to show you that if you take a measurement of the V open circuit, okay, if you just measure V open circuit for the solar cell, but under different irradiance, from there you can also extract the new information. Okay, you can also see some new information actually from these measurements. So we would like to actually show you what are the measurements that you can perform on your solar cell that will let you learn new things or new insights actually into your into how you can improve your solar cell performance. Okay, and typically whenever we offer this chapter, typically we'll also try to do a lab demonstration that involves some of the equipment we have in the lab. So for this part, I don't think we can physically do that this semester, but as some of you have suggested, maybe I'll try to ask the lab engineer to see whether he can provide, maybe he can record the videos from the equipment, so that you can actually see them directly, through the video. Okay, and if we still have time, I'm thinking to run the 1 or 2 tutorials on some useful software. So Origin Lab is one of the software I have in mind. At the same time, for our projects, I also have another software in mind, that is the GPVDM software that will let you actually simulate the performance from a solar cell. Okay, that is actually very useful for our course. So I'll actually keep this in mind. I think at some point I may ask you to install the software, and then from there we may do a 1 or 2 class that is a tutorial based on this kind of softwares. Okay, so I hope this is clear with you. So let's start. Okay, let's start from for this chapter. So the first topic we would like to mention today is actually the measurement for the efficiency measurement for solar cells. Okay, the efficiency measurement for solar cells. So as we learned from before, I think the standard that we typically use to measure the solar cell is the STC, the standard test conditions. Okay, what is included in the typical standard test condition requirements? We typically have three basic requirements. Okay, requirement number 1 is that the overall irradiance intensity, it should be 1,000 watt per square meter. I'm sure that this is the most familiar to all of you. And then the second requirement is that the light spectrum, the solar spectrum, or the spectrum from the light source, it should follow AMS 1.5G. Okay, which stands for AMS 1.5 global spectrum. And then the last requirement is that the PV temperature or the module temperature, it should be 25 Celsius constant. Okay, so it seems to be a very simple set of requirements, given that we have only 3 sentences here, 3 requirements. But in reality, in practical measurements, it's actually not that easy for you to achieve these 3 requirements. Okay, so the first 2 requirement is specifically related actually to the light source. Okay, to the light source. While the temperature requirement is related basically to your measurement system. Okay, to your measurement system, how we can achieve a constant 25 Celsius in the measurement system. Okay, and even for the light source, if you want to find the light source, that will give you precisely 1,000 watt per square meter at the same time with the AMS 1.5 global spectrum. It's not that easy to do. Okay, it's not that easy to do. You might be wondering, should we, or can we use directly the outdoor, sunlight to do the measurement? Can we use the real sunlight to do the measurement? This is actually not that easy. The problem is that the outdoor or the real sunlight, typically it is fluctuating. Okay, it is fluctuating quite a bit. And if you have clouds, in the sky, if you have, some kind of air pollutions, the chances are the sunlight passing through these clouds or these pollutions. Also, the shape of the solar spectrum is going to change before and after. Okay, so this actually will not give you a precise AMS 1.5 solar spectrum as defined in the standard. Okay, and the radiance is not going to be a constant, a perfect 1,000 watt per square meter. And given that, we're from our efficiency calculation, we know that for one thing, the solar cell current, it is directly proportional to irradiance. So any fluctuation in irradiance or any change in the spectrum, this actually will directly affect the efficiency you got from there. Okay, so this is actually quite important for you to know that because of these reasons, we typically cannot afford to use a real sunlight as the standard to test a solar cell. There are too much variation, too much variance involved. Okay, so in the lab, typically how this is done, typically we prefer to use a indoor measurement with the artificial light source. Okay, with an artificial light source. So this artificial light source, it is called a sun or a solar simulator. Okay, with this solar simulator, we can produce actually artificially a simulated sunlight that would be a much better fit to the STC conditions compared to actually the outdoor sunlight. Okay, and then also I just want to point to something here. That typically we have to follow a lot of small requirements in the indoor measurement to make the measurement as precise as possible. Okay, so for one thing, you can notice that this is the solar cell holder for the solar cell to be tested. At the same time, for the surface that is from the solar cell that is actually below the solar cell, we actually painted the solar cell black, so that we have a minimum reflection. Okay, minimum reflection. Minimum reflection means that you have a minimum chance of light reflected into the solar cell, because any reflected light, they will add to the irradiance. So ideally, you may have a 1,000 watt per square meter from the simulator, but then with the reflected surface reflection, you may have a more than 1,000 watt per square meter irradiance. So in the real measurement, you have to pay close attention to all these details to minimize the errors, to minimize any kind of accidental factors. Okay, so that is actually I think quite important for you to know before you step into the measurement domain. So we mentioned actually this before. I mean the correlation between the spectral irradiance and the irradiance before in solar PV. So I don't think we need to talk too much here. But in general, for a certain light spectrum, for a certain light source, there are two parameters you have to focus on. Okay, obviously you have to focus on the watt per square meter irradiance, but at the same time, the color of the light source, the property of the light source, it is also coming from the spectral irradiance. Okay, spectral irradiance is essentially irradiance plotted versus wavelength. Okay, plotted versus wavelength. So here we have the EMS 0 spectrum. Okay, that shows you that at a certain wavelength we have a certain intensity. At this wavelength, and then we have the EMS 1.5 spectrum. Okay, that shows you a different spectral irradiance. That shows you a different shape of the spectral irradiance. And because of the different shape, we consider these two light sources are completely different. Okay, they are completely different. The color will be different. The property will be different. And if you consider together with the silicon semiconductor, the performance you get from the silicon semiconductor, it will be different. Okay, even if somehow they have the same irradiance, they have the same watt per square meter, they will not give you the same performance in solar cell, simply because they have a different wavelength behavior. Okay, and what is the correlation between the spectral irradiance and the irradiance? Well, from the spectral irradiance, if you do integration versus the wavelength, the area under the curve, that will give you the overall irradiance from the spectrum. Okay, so if you want to find out about the irradiance from a certain spectrum, okay, as a function of lambda, you just have to integrate with lambda, okay, against lambda, from the start of the spectrum to the end of the spectrum. So from this point, basically that covers all the way to the end of the spectrum, and then the area under the curve, that will give you actually the irradiance. Okay, that will give you the irradiance, which is in watt per square meter. Okay, watt per square meter. So that is actually important for you to know here, right? And here we have some examples from different air mass spectrum. Okay, so that you can have an idea. So for instance, the air mass 0 spectrum, if you do integration of air mass 0 based on the ASTME E490 standard, the space spectrum will give you about 1,353 watt per square meter intensity. Okay, this is actually very close to the solar constant value that we mentioned back in solar PV. Okay, and then we have we have a different other spectrum here. The most obvious spectrum is definitely the AMS 1.5G. Okay, you can see that in certain standard, the AMS 1.5G does not integrate to 1,000 watt per square meter exactly. In this standard, it's actually integrated to 963. But then in another more commonly used standard, the shape is the same, but then we just raise the intensity slightly. So it becomes a nicer 1,000 value for the irradiance. And as we know, 1,000 is easier to handle for calculation. So that's why we typically prefer the 1,000 watt per square meter version of the irradiance. Okay, so this is actually the different standards that we may find in solar cell measurements. Okay, so obviously depending on your application, you may need to turn to different standard, different solar spectrum. For instance, if you have the goal to design solar cells or solar PV for space application, then your starting point, it should not be AMS 1.5 because this is the surface solar spectrum. You should turn to, for instance, AMS 0 spectrum that is more representing of the space solar spectrum. Okay, and in the space, we know that before the sunlight enters the atmosphere, we have a very different spectrum behavior in the spectrum irradiance. Okay, so some wavelengths before the atmosphere, they will not be decreased because of the atmosphere. And in the space application, like these features are actually more important for your measurement. Okay, so that is the solar spectrum. So let's consider actually a question here. If we have a silicon solar cell, okay, and we basically expose the silicon solar cell to two different light sources, okay, to two different light sources, and somehow the two different light sources, they have the same irradiance, but the spectrum irradiance, the shape of the spectrum is different. The question is, will the IV response you get from the same solar cell still be the same, or they will be different? Okay, will they give you the same output if you have a two spectrum with the same irradiance but different shape? Okay, so I'm sure you can already guess the answer. They will not give you the same performance. Otherwise, we do not have to go through so much trouble to define the AMS solar spectrum in the STC. Okay, the performance difference has to do with the semiconductor behavior. Okay, actually this graph is actually is something we mentioned back in solar PV. I'm sure you're very familiar with this graph by now. Because the silicon is a semiconductor, and also practically all the solar cells are based on semiconductor. And for any semiconductor, based on the band gap, we can always find the cutoff wavelengths. Okay, so for instance, for silicon, the cutoff wavelength is around 1,100 nanometer. So this means that the cutoff is actually precisely here. Okay, this is the cutoff for silicon. Okay, and then as we said last time, if the incoming photon compared to the band gap has a certain amount of energy difference, at this time we may need to consider the thermalization losses. Okay, especially if the incoming photon has a very high photon energy. At this time, you're going to suffer more thermalization losses because, as we said, the incoming photon will excite the electron to way above the band gap, and then immediately the high energy electron will relax actually into the edge of the band gap, edge of the conduction band. Okay, so in this way, that part of energy losses will be the thermalization losses. Okay, so the problem is that if you have a different spectrum sensitivity, or sorry, if you have a different spectrum irradiance, you are going to end up with the different thermalization losses. Okay, and also, if the spectrum irradiance is also different in the long wavelength region, you may also have a different transmission losses. Transmission losses means that this part of the spectrum, it cannot be absorbed, it cannot be used by silicon completely. Okay, so basically the efficiency coming from this part is going to be 0%. You cannot generate any electricity from actually from the long wavelengths that's above the cutoff wavelengths. Okay, so given this consideration, if we consider two light sources, right? For instance, one is the air mass 1.5 spectrum, and then if we have another light source, right? That is a completely different, that has a completely different shape. But maybe if you run integration, they have the same area, and then you can actually already see from here, because the second spectrum has way more transmission losses compared to the first one. So obviously the performance from the second spectrum, from the long wavelength spectrum, is going to be significantly lower compared to the air mass solar spectrum. Okay, that should be something very easy. That should be something very easy for you to see, from our discussion here. Okay, and then let's consider some extreme scenarios, extreme cases. Okay, so for instance, if we have a one light spectrum that consists of a purely 600 nanometer photon. So 600 is roughly here, right? 600 nanometer. So we know that in this region, the silicon solar cell will respond very strongly to the photons here. Okay, and then the other spectrum contains only 1,200 nanometer photon. So the spectrum irradiance is something like this, right? Well, the first one is something like this. So they may have the same irradiance, but then what's going to be the performance from these two spectrum, from these two single wavelengths spectrum? Okay, you can try to think about that. So let's start from the long wavelengths. For the 1,200 nanometer photon or spectrum, what's going to be the performance from a silicon solar cell? Obviously, because this 1,200 nanometer is beyond the band gap or beyond the cutoff wavelengths. So obviously, all the irradiance here, all the spectrum irradiance, they will go to transmission losses. Okay, they will go to transmission losses, meaning that you will not be generate any carrier from the second spectrum, from the 1,200 nanometer spectrum. Okay, so essentially your current density generated from here is going to be 0 for the second spectrum. Okay, what about the visible spectrum? What about the 600 nanometer spectrum? Well, in that case, we can try to make use of the quantum efficiency concept we talked about in the last chapter. Okay, so suppose that in the 600 nanometer spectrum, suppose we have a precisely 1,000 watt per square meter irradiance. Okay, and for the quantum efficiency, if you want to use the quantum efficiency, we know that the quantum efficiency EQE equals the number of electron and hole pairs divided by the number of photons. Okay, so from the graph down here, we have the quantum efficiency behavior from a typical silicon solar cell. Okay, so you can try to focus on 600 nanometer scale. Okay, on the 600 nanometer wavelengths. How much is the quantum efficiency here? This is the EQE. Okay, how much is this? Let's assume that this is a 64%. So this means that if we can somehow find the number of photons at this wavelength combined with the 64% quantum efficiency, we should be able to find the number of electron and hole pairs. Okay, so first of all, how do we find the number of photons here? Very simple. The number of photons per second, right, equals the irradiance, which is a power density, divided by the energy of 1/600 nanometer photon. Okay, so if you do the calculation, the photon energy equals a Planck constant, okay, times the speed of light divided by lambda. So this is going to be 2.06 electron volt. Okay, electron volt is a very small unit. And then if you take 1,000 watt per square meter divided by that, remember you have to convert this to joule. Okay, to joule. You can find that for the 1,000 watt per square meter irradiance, we do have a large number of photons coming in per second and per meter square. Okay, so per second per meter square, we have this amount of 600 nanometer photons incident on the solar cell. Okay, so how many of these photons can we convert into carriers? Well, we just simply need to use the quantum efficiency we found from the graph. So 60%, 64% of these number of photons, it will be converted eventually to electron and hole pairs. So how much is that, right? This is the number of charges, okay, number of carriers. And then how do we go from number of carriers into current density? Very simple, multiply by Q, because one carrier will give you one charge of Q, okay, one unit charge of Q. So if you multiply together, they will become current, because we are talking about charge per second, okay, we're talking about charge per second, and charge per second automatically becomes ampere. Okay, charge per second becomes ampere. And remember, typically for current density, we prefer to use this unit. So you need to do a sort of a conversion to match the unit here. But as you can see, the final value, the final current density is about 30 milliampere per centimeter square. Okay, do you guys still remember what was the current density or short circuit current density for the champion silicon solar cell we just talked about in chapter 1? It was 42 something. Okay, 42. Yeah, very good. And yeah, it was a 42 something. So with this irradiance, actually, we're getting a very good performance from the silicon solar cell. Okay, it was a 30 something. But remember, typically we cannot compare directly between the two, because the 30 something current density is measured under a very special spectrum. Okay, while the 42, it is measured from the AMS 1.5 G STC condition. So you cannot compare directly, but at least this will give you an idea about the performance that you are getting from the silicon solar cell. Okay, so that is actually the importance of the light source spectrum irradiance. So basically, you can see. I hope that you can begin to see why we need the two sentences. We need the two requirements in STC to define both the irradiance, to define both the watt per square meter, as well as the spectrum irradiance, the AMS 1.5 G spectrum. Okay, so that is basically the job for solar simulator. It is used to simulate the accurate STC requirements. Okay, not only the irradiance but also the spectrum irradiance. Okay, also the spectrum irradiance. So that is the idea here. All right. So we need to, in solar simulator, obviously there should be some kind of a light source inside. So typically, what are the possible options? What kind of a light source we can incorporate into a solar simulator? Okay. So these are the common options typically. The best option typically, or the most popular option, is the so-called xenon arc lamp. Okay, xenon arc lamp. This is the most widely used option that will provide you with the very accurate, or with the very close, very similar. They'll produce a very similar spectrum to the AMS 1.5 G. Okay, but then the problem is that this kind of light source is usually more expensive compared to the other options. And then before a lot of solar simulators, they make use of the metal halide arc lamps. Okay, so these lamps are cheaper, and also they provide a very stable output. But the problem is that the spectrum you get from the metal halide lamp, they are not that similar to the AMS, to the standard AMS spectrum, and therefore you need to do more modification on the spectrum so that it can fit better with the solar spectrum. Okay, and then before, another popular option was the halogen lamp, was the tungsten halogen lamp. These lamp actually they also produce a spectrum that is usually different compared to the sun, compared to the solar spectrum. Okay, because we know that for solar spectrum, typically you're talking about a yellowish light color. So if you look at the solar spectrum, the peak usually it is around the yellow color. Okay, but then these halogen lamps actually typically they produce a lower color temperature, meaning that overall the light will have a slightly different color. Okay, and the peak of the spectrum is not exactly the same as the solar spectrum. Okay, and finally, in recent years, we have also solar simulator made using the light emitting diode light source. Okay, LEDs. LEDs, as we know nowadays, is very popular in lighting applications because they consume low power and they have a very long lifetime. Okay, but then with the LED, there is a very critical limitations. So actually in solar PV, when we first mentioned solar cells, we also mentioned LEDs at the same time. Okay, if you remember, actually, I believe I said about this that the LED it is very similar to solar cell in many ways. Okay, so what can you tell me about LEDs? Why the LED is emitting light? Based on what the LED is emitting light, as a light emitter. Well, both of them they are based on semiconductors, so definitely there is a band gap involved. Okay, and in many ways, these two devices, they're similar to each other because actually they are sort of doing the reverse process. They're basically doing the reverse process compared to actually the other guy. Okay, so for solar cell, we mentioned that you have the excitation process, with the incoming light. Okay, and then after the separation, you get the current coming from the solar cell. Well, for LEDs, the opposite. We still have a semiconductor involved, but then instead of extracting current, instead of getting current, we inject current into the semiconductor. Okay, so we're going to inject a lot of electron from one side, a lot of holes from the other side. Okay, and then they will meet at the center in the emission layer. And in the emission layer, instead of having excitation, the electron will actively recombine with the host. Okay, and in doing so, the electron has to lose energy, and this amount of energy losses here, it will be released as light emission. Okay, it will be released as a photon, basically. Okay, so that's why they are very similar to each other. And then if you think about it, as the light source for solar simulator, what is the limitation for LED? So let me ask in another way. Can my solar simulator use only one single LED to produce the solar spectrum? Why or why not?
No, we can't.
Okay, yeah, tell me more.
Yeah, because each physical LED will only be able to produce one particular wavelength.
Yeah, very good, very good. Yeah, that's a very good answer. If you see from actually the plot here, how much energy we are losing for this specific LED, for this specific semiconductor. Actually, the amount of energy released is precisely the same. Okay, it is fixed to a single value. And ideally speaking, like solar cell, if you have a one recombination happening, ideally speaking, you release one photon. Okay, you are going to release one photon, and then this band gap energy, it will be translated into the photon completely. And if you define the band gap energy, then the wavelengths that you calculate from here, it's going to be a fixed wavelength. Okay, it's going to be a fixed wavelength. So the conclusion is that from one LED, typically you get just one color. Okay, you will get the one single color from one LED. And if you did any circuit measurement before, and if you use any small LED before, you will actually see this phenomenon. Okay, one single LED will produce just one peak in the spectrum. Okay, one peak in the spectrum irradiance, and that is a problem for solar simulator because typically we know that the solar spectrum has a very wide range. So in this case, if we really want to use LED in solar simulator, what do we need to do? Instead of one single LED, we have to use a cluster of different LEDs, okay? That together they can produce a spectrum very close or very similar to the actual solar spectrum, Okay, so that's basically what is written here. We have to go to clusters of LED. But then the problem is that if the number of LEDs is too small, okay, instead of having a smoother spectrum, you are going to end up with something like this. Okay, so you need to find a balance actually with the cost of the solar simulator and the performance. If you use more LED, you will get the smoother solar spectrum, but your solar simulator is going to be more expensive. Okay, so these are the different options typically we can find. Okay, and here we're showing you a typical design for a solar simulator. Typically at the end, we prefer this, the simulated light to come actually vertically from up to down. Okay, the reason for this is that it's easier for you to put the solar cell here to do measurement, and then you don't have to worry about the solar cell moving or the solar cell falling. Okay, so you can align the solar cell easily. And then typically within a certain area, the solar simulator will produce a very uniform and a very good, light illumination here that will be as close to the STC requirement as possible. Okay, so this simulated light typically will come from actually a light source inside the solar simulator. And in order to do the vertical incidence, typically we have to use a mirror, reflectors to control the direction of the light. Okay, and then even with the best lamp, even with the xenon lamp that we mentioned before, it's not enough for xenon lamp to completely simulate the solar spectrum. Okay, so this means that we have to do correction on the spectrum from the lamp that we are using. So this typically means some optical filter. Okay, optical filter. We're going to use the optical filter, for instance, to trim the light spectrum. If your light spectrum is like this, and then after the filter, we will be removing some of the peaks and make it smoother. Okay, and make it smoother. So this is typically the idea. And then here we also have the lenses. That's called the collimating lenses. The idea is that from the light source, actually the direction of the rays, they're not exactly parallel to each other. Okay, you may have a rays going in all the directions. And then the problem is that if you don't actually control the direction of the light rays, then this is going to be a problem, because when they come down to the solar cell, if they're parallel to each other and you put the solar cell here, the radiance you are getting is going to be relatively constant. Okay. However, if they're going in different directions, that's basically not collimated, then the solar cell you put here versus the solar cell you put there at the different depths, you are going to have also very different irradiance. So the irradiance basically will go up or go down depending on the height. Okay, and also locally speaking, if you don't have the collimated light, the irradiance you get at this point is going to be very different from the irradiance you measure at another point. Okay, so it's going to create uniformity issues for you. So for solar cell, typically we have that's why typically we would like to have the collimated requirement. We need to collimate the light so that the light after the lenses is going to go in parallel with each other, and then you have a very uniform incidence. Okay, and then as we mentioned, before that, typically we also need to use the AMS filter to correct the light spectrum from the lamp. Okay, so that is the idea for the solar simulator. Okay, so let's show you one example. Okay, let's show you one example. So this here, the dash line here, or the dotted line here, the red line, is actually the emission from a solar simulator lamp. Okay, from a solar simulator lamp, the sun simulator lamp here, and then the black curve is from the AMS 1.5 spectrum. So you will notice for many light sources, you are going to see these spikes from the lamp. Okay, but then if we want to simulate the AMS spectrum, then this is why we have to use a typically additional optical filter, basically to remove this peaks or spikes that you see from the lamp. Okay, these spikes, naturally it cannot be avoided, but with the better filter, we will be able to trim down these spikes, and then we're going to have a better fit with the AMS 1.5 requirement. Okay, so this is the idea. And then here is an example of the xenon lamp that is used for IMAX projection. And this is the emission from the xenon lamp. You can see that we have a lot of spikes here that you are not going to find in the actual solar spectrum. And also we have some spikes here. And maybe the shape is not the same. So which is why we have to send this actually through the optical filter, okay, through the optical filter to basically to modify the emission so that it's as close to the solar spectrum as possible. Okay, so I think we can stop here. Do we have any questions before we conclude today? Anything that is not clear, guys? So far, so good. Oh well, okay. In that case, I think that's it for today. Thank you for participating in today's lecture, and I'll see you on Thursday. Okay, you can log off now. Thank you, guys.